So we talked about conservation momentum and this idea that the momentum of a system and the system center of mass will stay constant as long as there's no external forces acting on the system. One of the big applications of conservation momentum that comes up in physics and our study of the universe are these things called collisions. So two bodies come together, they collide, and to simplify things, we'll assume that they do one of two things, that they'll either bounce off of each other or they'll stick together. Okay. Honestly, real collisions, fall somewhere in between. They'll kind of deform and stick together, but they'll also bounce off each other a little bit. But we'll simplify things like we, usually do in this course, and we'll just consider, those two extremes. So when we talk about these two extremes, the one extreme is this inelastic collision. So if we have, say, rail cars, right? And so we have our cars, and maybe there's like a magnet on the end of it. And then we have another car, and there's a magnet on the end of this car. Okay. And they come together. What's going to happen is that these are going to stick. Okay. So one car is moving. Maybe this is initially at rest. And then they stick together. And when they stick together, they're going to have some different velocity. So if we call this velocity V naught, these two cars stuck together will now have some different velocity. It's going to be less. Let's just call that V prime. Okay, so they're going to move off. Now, they're stuck together. This is an inelastic collision. Now, in an inelastic collision, only momentum is going to be conserved in this. The system has some kinetic energy at the beginning. We call this KE initial. And it's going to have some kinetic energy at the end, KE final. But what we'll see is that the two will not be equal to each other. Okay, so when objects stick together, the kinetic energy of our system changes. And what happens is that some of that initial kinetic energy got dissipated in the form of heat. If you have two clay balls, a lot of that energy is going to go towards, deforming the balls. If it's in a case like this, some of that energy is going to be spent, with the attraction. It's going to be those two magnets are going to attract each other. They're going to stick together, and some of that kinetic energy is going to be dissipated as they cling together. So, that's the big thing. But it kind of makes it nice because initially we have two possible momenta. Our momentum of the system is the sum of the momenta of all the objects in the system, and initially we have two different objects, so we could possibly have two different momenta, especially if this boxcar is moving. Afterwards, though, once they're stuck together, the mass of the system is the sum of the two masses. We only have one object moving away, and so that does tend to simplify things when we think about these situations or we work problems with them. Okay, so that's one situation, an inelastic collision where the two objects will stick together. The other extreme is they don't stick together. They bounce off of each other perfectly, and they do so without any loss of kinetic energy for our system. Now remember, kinetic energy is a vector quantity. So maybe I have some ball moving that way, call that V1, and maybe I have another ball right here and it's moving that way, call that V2. Our system has some net kinetic energy to it, and it would be the sum of the kinetic energies. So 1 to 2. So it would be the sum of the kinetic energies of everything in there. And so they bounce off of each other. Okay, so they kind of, they collide, they're not together. And then, and this doesn't always happen, if they have the same mass, that's going to happen, is that's going to go off that way. So let's call that V1 prime. And the other goes off this way. Okay, call that V2 prime. Okay, and it's going to have some final kinetic energy. And once again, we can say It's the sum 1/2 vi prime squared. All right. And what we'll find with this is that these two are going to be equal to each other. Okay, the final kinetic energy of the system, our initial kinetic energy of the system, will be equal to each other, and momentum is also conserved as well. So when we work these types of problems, we'll have two different equations that we can use, two different conservation law that allows us to solve for things. One conservation law is from the conservation of momentum, and this would have the form, m1 v1 plus m2 v2 will equal m1 v1 prime plus m2 v2 prime. Okay, so it's going to kind of have that form. And then we also have this conservation of kinetic energy. So 1/2 m1 v1 squared plus 1/2 m2 v2 squared will equal 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. All right, so these, it's nice that the kinetic energy is conserved and all, but the algebra can get kind of gnarly on it. The algebra can get kind of gnarly because we have potentially four different variables. We can have the two different masses, we can have the two different initial velocities, and we have the two different final velocities. Okay, so these problems do tend to be more algebraically complex, but conceptually at least, just keep in mind that for elastic collisions, when things bounce off of each other, that both the kinetic energy and the momentum are conserved. So what I want to do in class is go through a couple sample problems involving these types of collisions, kind of show you how the mathematics on it works, and we'll go over some conceptual questions as well.